Patrick Hopper, the science dude. On today's show, radioisotopes and their uses.
Hi, and welcome to the Science Show. I'm going to be your professor for today, Patrick Hopper. And today we're going to learn about radioisotopes and their many beneficial uses in society. But before we do that, we need a timeline of events today on the show.
And the outline for today is we will start with a brief overview of radioisotopes, then move to how they are used in smoke detectors. Next we will learn what carbon dating is, followed by what food sterilization is. Finally, we will end the show with radioisotopes and their use in medicine. If you want to read more about them in the textbook, they can be found in page 37 to 38 and 142 to 146.
Isotopes are atoms of the same element that have the same number of protons and electrons as the other atoms, but differ in the amount of neutrons they have, causing a different atomic weight for each isotope. There are radioactive isotopes, or radioisotopes for short, that have the tendency to break down and decay, releasing energy in subatomic particles in a process called radioactivity. This process continues until the atom becomes stable by becoming an entirely new element by losing subatomic particles. There are three main types of decay that a radioisotope would go through to become stable again. The first type is alpha decay, as we can see here on the blackboard. So the radioisotope emits something called an alpha particle, which is essentially, as you can see down below here, a helium atom with 4 protons and 2 electrons, and this causes it to become stable. The radiation emitted from this type of decay is very weak and can't even penetrate through paper, making it safe for humans to be exposed to. The second type of decay is called beta decay, where a radioisotope emits an electron seen here, represented by a 0 over -1, its charge, and the letter E. But as we can see here in our model equation, hydrogen becomes helium during this process. That's not possible by losing an electron. So while this process occurs, one of the neutrons also becomes a proton, causing a new atom to be formed. Beta decay is stronger than alpha decay as it can penetrate paper, but it can't penetrate most objects such as wood or even human bone. The final type is gamma radiation. This type of radiation usually accompanies the emission of an alpha particle or beta particle. As we can see here by our model equation, this one's accompanying a beta particle, or the emission of an electron. Now, because it has neither mass nor charge, gamma radiation is represented by 00 over Y. This type of radiation is the most harmful to humans, and it can only be blocked by big pieces of lead. One of the greatest uses of radioactive isotopes is that of the common smoke detector to help warn us about fires and help us safely evacuate buildings. There are two types of smoke detectors, a photoelectric smoke detector and one that uses radiation. This is the better of the two because it's able to detect a wider range of fires and is generally less expensive. And here we can see the interior of the common smoke detector with one of the most important structures being here, called the ionization chamber. Named so because it's where the radiation is produced and stored. There's a small disc in here, about 5 millimeters in size, which is smaller than a dime, called americium-241, which is the radioactive isotope used in smoke detectors. There's small holes in its surface which allow oxygen and nitrogen to flow through and react with the alpha particles produced by the disk to form charged ions. These ions are then collected by a low voltage current. With the current established in the smoke detector, when smoke enters the ionization chamber through the tiny holes, it reacts with the alpha particles produced and absorbs them. This causes the ions to not be produced and the current to falter. It is this faltering of the current that causes the alarm to ring out and bring notice to people that there is a fire nearby. With most of the alpha particles either absorbed by the smoke or released harmlessly because of the low levels of radiation, smoke detectors do not pose a risk to our health. You can even swallow the 5 millimeter disc of americium and not be exposed to enough radiation to significantly harm you. There it is! Hi everyone, I'm an archaeologist, and it's my job to find organic pieces of matter from long ago in order to learn more about the past. But when I do, I often have trouble identifying the age of the object. But radioisotopes can help us by telling us the age of many different things in a process called carbon dating.
Carbon dating involves the use of a radioactive isotope of carbon called carbon-14, which is produced naturally in the atmosphere. First, cosmic radiation emitted by a celestial object, such as the sun, hits an atom, causing it to become an excited neutron. This excited neutron travels in many different directions until it collides with a nitrogen-14 atom, causing a proton to be displaced, a neutron to be captured, and carbon-14 to be formed. It then reacts as normal carbon with oxygen to form daily compounds that we use in our everyday lives. Carbon-14 forms a 1-to-1 ratio with the most common isotope of carbon, carbon-12, and through daily activities such as breathing and eating, human beings and animals can take in and replenish their amounts of carbon-14. However, following death, they're no longer able to take in carbon-14 and it starts to decay back to nitrogen-14. The half-life of a radioactive isotope is the amount of time it takes for an amount of an isotope to decay to half of its original amount. For carbon-14, it is 5,730 years. With this information in mind, scientists can study the ratio of carbon-14 to carbon-12 in the body of an animal and determine how much of the sample of carbon-14 is left, and therefore how long it has been dead for. This poses no risk to human beings and animals or the environment because carbon-14 is very low dosage and it only emits alpha particles which pose no harm to any environmental aspect. Hello, and welcome to the Science News. On tonight's show, we have an in-depth analysis of how radioactive isotopes can be used to help treat our food and make it safer to eat in a process called food sterilization. Now, if you don't already know, food sterilization is the process by which microbes and other disease-causing bacteria is removed from our food in order to make it safer for us to eat and extend its shelf life. The process begins by placing food in bulk on a conveyor belt, which then brings it into a device called the radiation chamber. Once it's in the radiation chamber, it passes under a radiation beam similar to a light beam emitted by a flashlight. Once underneath the radiation beam, it is exposed to ionizing radiation which attack and destroy the microbacteria on the food. It does this by affecting their cellular processes, such as the way they reproduce, causing none of the bacteria to be able to reproduce and eventually die out. The most common isotope used for this type of radiation is cobalt-60, which is a radioactive isotope of cobalt. It is used because it is generally easy to get and poses little risk to humans or the environment because it emits alpha particles. It is stored as pencil-like rods within the radiation chamber, which then is converted into the radiation beam. It has a half-life of about 5.3 years and decays into harmless and normal nickel once it's done. And to end the show today, we have a PowerPoint presentation about radioactive isotopes and their uses. The thyroid gland is an important gland in the body of every human being because it is responsible for producing the hormones that regulate the body's metabolism, which is the rate at which we burn up food. So essentially, it is important because it controls our weight and body image. But in radioiodine therapy, where radioiodine or iodine-131, the patient swallows a small amount of the radioactive iodine and it is then absorbed into the bloodstream by the gastrointestinal tract. After being absorbed into the bloodstream, the radioiodine atoms travel to the thyroid gland where they emit radiation and destroy its cells. While this is generally viewed as a bad thing, radioiodine therapy can be used to treat thyroid cancer or hyperthyroidism, where the thyroid is overactive and produces too much hormones, and it can treat these disorders by destroying the cells that cause them and eliminating it from the body. However, it does destroy parts of the thyroid and leaves the patient without part of it for the rest of their lives, so follow-up procedures are needed to ensure the patient can live a healthy life afterwards. Another important use of radioactive isotopes is in cobalt therapy, where cobalt-60, an isotope of cobalt, is used to destroy cancer cells and tumors in the body. The way it works is the patient lies down on a machine where a small cylinder of cobalt-60 releases gamma rays which travel through a device called the collimator in JAWS, which direct the beam and ensures it hits the target area of the patient. The cobalt-60 beam strikes the part of the person where the tumor is located and affects the cancer cells by stopping them from being able to reproduce by affecting their cellular processes. However, the beam can have dire consequences for healthy tissue because it uses gamma radiation which can seriously affect the healthy tissue and even cause new cancer cells to be formed. To avoid this, the beam rotates at many different angles to avoid damaging the tissue and uses precise measurements to expose the patient to as little gamma radiation as possible. Now, Canadian connection to all this medicine is that Canada produces over 80% of the world's cobalt-60 and treats 500,000 patients each year using cobalt-60 cancer treatment, or the cobalt bomb. Also, Canada produces about 30% of all radioactive isotope processes for the world to use.